This is a video lecture for Math 283, and the topic today is the calculus of vector functions. This is section 13.2 in the textbook. In section 13.1, we defined what a vector function is, whereas with a regular function, you have an input of a real number and you get an output of a real number. With a vector function, you have an input of a real number and your output is actually a unique vector. Now, most of calculus 1 and 2 dealt with applying calculus to regular functions. So how do you take a derivative of a regular function? How do you take an integral? Well, now we'd like to learn how to do calculus on vector functions. How do you take a derivative of a vector function? How do you integrate a vector function? The good news is the methodology we've already learned is very analogous to vector functions. So this will not seem new to you guys. There's a few small differences. So let's talk about how do you take derivatives. Let's start with the derivative. How do you take a derivative of a vector function? Well, the derivative of a vector function, so dr dt equals r prime of t is equal to the limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t. This is the definition of the derivative of a vector function. Now this is very similar to the definition of a derivative of a regular function, if you guys recall that. Okay. What does this mean graphically though? So I've created a graph here, a 3D graph of some kind of space curve r of t. Okay. And we have 2 points along this space curve, p and q. And I've created position vectors from the origin to each point. So let's imagine point P applies at a time t and point Q applies at a time t plus delta t. So here we have r of t connects the origin to point P. We have r of t plus delta t connects the origin to point Q. Okay? And by the rules of vector addition and subtraction, I can create a vector, a secant vector from point P to point Q that's r of t plus delta t minus r of t. Okay, and what happens here as delta t becomes small? As the interval delta t shrinks to 0, this point q approaches point p. Okay, and this secant vector becomes shorter and shorter, but this vector also becomes the tangent vector to the space curve r of t at point p. So let's write that down. As the interval as delta t shrinks to 0, then the vector PQ, which is equal to r of t plus delta t minus r of t, becomes the tangent vector to the space curve r of t at the point P. Okay, so this secant vector becomes a tangent vector to the space curve r of t at point P. Okay. Well, if this is a tangent vector, then any scalar multiple of this is also a tangent vector. Specifically, the scalar multiple of 1 over t times r of t plus delta t minus r of t. This is also a tangent vector to the space curve at point P. Well, what is this? This is just our derivative in the limit as delta t approaches 0. So basically, the conclusion of this is that this derivative here, the derivative of our space curve, is the tangent vector of that space curve at the point P, which applies to a time t. So it's very analogous to a regular function, whereas the derivative of a regular function is the slope is the tangent line, or the slope of the tangent line to that curve at the point P. The derivative of the space curve is the tangent vector to the space curve at the point of interest. We also can talk about a unit tangent vector. So we'd like to find the tangent vector that only has a magnitude of 1, and you can find this simply by taking r prime of t and dividing by the magnitude of r prime of t. So this is our unit tangent vector. That may be useful sometimes. Now, as far as rules, as far as taking derivatives, Here, hopefully you guys can see the other side of the board. I'll just reposition this camera a little bit over there. Let's talk about how you actually take derivatives. So if you're given some vector function r of t equals f of t I plus g of t k j plus h of t k. Okay, the good news is if you want to take the derivative of a vector function, you take the derivative of each component. So r prime of t equals f prime of t I plus g prime of t j plus h prime of t k. Okay, so that's a simple rule for how we take a derivative. Let's do an example problem here. Let me just migrate this example problem over a little bit because I know it's easier to see on this side of the board. So here's an example problem. Let's say you guys are given the function r of t, the vector function equals sine of ti plus t squared minus 1j plus natural log of tk. Okay, how do we find the derivative of the vector function here? R prime of t, we just take the derivative of each component. So the derivative of sine is cosine of t I. The derivative of t squared minus 1 is 2t j. And the derivative of natural log of t is 1 over tk. So this is now our the derivative of the vector function. Let's try to find the tangent vector. So that's part A. Let's do a part B here. Let's find the tangent vector. Tangent vector at t equals 1. So when the parameter t equals 1, what is the actual tangent vector to the space curve r of t at that time? Well, all we do is we plug in t equals 1. So r prime of 1 would equal cosine of 1, which actually comes out to, let's write that out, as cosine of 1. You have to use your calculator to figure that out, I, plus 0j. And then the k part, excuse me, or am I doing t equals 1 or 2? What was I doing in this example problem? That's 0j plus 1 over 1 plus k, right? And this comes out to 0.054. I just want to make sure I did this right. I had something slightly different in my notes. Oh, what am I doing here? I'm plugging in. I know what I was doing. I was plugging t into r of t and not r prime of t. So if I plug in t equals 1, I get 2j. And then I get 1 over 1, that's k. Okay, and you can calculate cosine of 1. This is 0.54. So this is our tangent vector to the space curve at that point. Okay, so that's differentiation. I want to mention one thing about the product rule. So we had a bunch of rules. If you guys remember in Calc 1, you learned a bunch of rules for taking derivatives of, this stuff doesn't erase as well, so it's like, that's okay. Maybe I need a different eraser. There were certain rules for taking derivatives. I'm not going to go through those rules because basically they're the same for vector functions, except the only difference is the product rule gets a little more complicated, or just has 3 different versions of it. Let's consider those versions. So if you have ddt of f of t times r of t. So what if you have some function of t, scalar function of t times a vector function? What happens here? We take the derivative of the first times r of t plus f of t times r prime of t. This is the same product rule you guys learned, but now we could have a scalar function and a vector function. So apply the product rule the same. What if you had ddt of r of t dot product with s of t? What if you want to take the derivative of 2 vectors, so the dot product of 2 vector functions? The product rule is the same here. So basically we take the derivative of the first, r prime of t, dotted with the second vector, s of t, plus r of t dotted with the derivative of the vector function s of t. Okay, so the product rule, the methodology is the same, but we have 3 applications of it versus 1. And then there's also, I'm not going to write it down, but there's also a curl version where you have r crossed with s. And the rule is the same for that too. Okay, as we've seen here, in the sense you take the derivative of the first crossed with the second vector plus the first vector crossed with the derivative of the second vector. Okay, hopefully that makes some sense to you guys. Let's talk a little bit about integration. Good news is with integration, we follow a very similar methodology as well as we did for regular functions. So if you have the integral from a to b of some vector function r of t, okay, you just take the integral of the components. So this is equal to the integral from a to b of f of t dt times the respective unit vectors plus the integral from a to b of g of t dt times j plus the integral from a to b of h of t dt times k. Okay, so we just integrate each respective component, and the fundamental theorem of calculus applies here as well to vector functions. So if we're taking the definite integral of r of t dt, then this is equal to capital R evaluated at b minus capital R evaluated at a, where r of t is the antiderivative of small r of t. Okay, that's the fundamental theorem of calculus. The moral here is the same methodology applies to vector functions, but we have to take the integral of each component. Let's do an example problem of this. So our final example problem of the video, example problem 2. Let's suppose we have the vector function r of t equals t squared I plus cosine of tj plus e to the tk. This is our vector function. Let's first do an indefinite integral of this. The indefinite integral, we're going to integrate each one of, so if we do the indefinite integral of r of t dt, we're going to integrate each one of these components. So this will equal the integral of t squared dt times I plus the integral of cosine of t dt j plus the integral of e to the t dt times k. Okay, and this is going to equal, if we integrate each one of these, we get t cubed over 3I plus sine of t j plus e to the t k. Now here we need to add an integration constant vector. So if you guys remember with regular functions, we had to add an integration constant for an indefinite integral. Here we have to add an integration constant vector for an indefinite integral of a vector function. And if we took the derivative of this vector would disappear. Let's talk about doing a definite integral. So imagine that we wanted to do this definite integral, 0 to 1 of this same vector function, r of t dt. Okay, well now we can use our result, and we can just simply plug in our limits here into this result, ignoring the vector function constant because now we have a definite integral. And if we plug in the limits here, we get 1/3 I hat sine of 1 minus sine of 0. Sine of 0 is 0, so we just get sine of 1 times j hat. This last piece, we have e to the 1 minus e to the 0. That's e minus 1 times k hat. And so now this is the integration, this is the integral of our vector function, the definite integral from 0 to 1. Okay, well this concludes our lecture video. I will see you guys tomorrow in class, and we'll do a number of practice problems in addition to this, more complicated example and practice problems.